Welcome back, everybody. Today's video is on the abelian variety attached to a primitive form, a concept we first encountered when looking at the fivefold theorem. Okay, so first the quotient ring attached to a primitive form. Let's let f be in prim to n. So remember, this means it's a Newform, which is also a normalized Hecke eigenvalue for all Hecke operators. We now associate to T, the Hecke algebra, a quotient ring T sub f. So associated to the Hecke algebra T for each primitive form f, there will be a quotient ring T sub f. All right, let's consider the ring homomorphism lambda f from T to the complex numbers given by the following equation: T of f equals lambda of f of T of f. So basically, lambda of f is spitting out eigenvalues of the Hecke operators. That's what's going on here for each T and T. And what we'll do is we'll set I sub f to be equal to the kernel of this map. Okay, and then the quotient ring attached to the primitive form f will be called T sub f, and it will just be T mod IF. So it's just the quotient of T by the annihilator ideal of f, basically. Okay, so let's give f a Fourier expansion with coefficients a of n. And let's recall that the number field of f is given by, we'll call it k sub f, and it's q adjoin all the Fourier coefficients a of n for each natural number n. Okay, so this we've already talked about. Now, if I get more specific with f, so if I give f a character chi, then lambda f does induce an isomorphism as follows. So kf, the number field attached to f, is isomorphic to take tf, the quotient ring attached to f, and tensor it up to q. These guys are isomorphic. And I can even give you the map. The map is, okay, so I'll go from left to right. So take tp plus if and send it to a of p, and send diamond of d plus if to chi of d. Very simple. Okay, and so you can see that what's going on here is the Hecke operators and the diamond operators kind of govern this side, and the Fourier coefficients and the character values govern the right-hand side. All right, so what's the abelian variety of a primitive form? Let's define a of f to be the abelian q variety associated to f given by, take the Jacobian j1 of n and just mod out by if times j1 of n. Very simple. Okay, so the action of t on j1 of n, remember j1 of n is the Jacobian of gamma sub 1 of n. Of x sub 1 of n. So we have a Hecke action on j sub 1 of n. We've known this for a while now. Now that action will induce an action of t sub f on a of f, right? So you have an action up top by t on j sub 1 of n. Once you mod out by if, by definition, you're going to get an action of tf on af. Because in the definition of AF, we're modding out by IF, and we're in the definition of TF, we're also modding out by IF. Okay, so, well, once I have an action of TF on AF, I have an action on each VL of AF. Why? Well, what's VL of AF, first of all? Well, first of all, remember what TL of AF is. That's the L-adic Tate module attached to AF. And VL of AF is just TL of AF tensored up to QL. And of course, once you have an action of TF on AF, you're going to have an action of TF on the Tate module of AF as well, because these actions will preserve various torsions. Okay. And then by tensoring up to QL, you maintain that action. That's all that's going on here. Okay. So there is an action of TF on the rational Tate module, the rational L-adic Tate module, I'll call it VL of AF for each L. Okay. So big proposition incoming here, but first a definition. Let's let K be a number field with a ring of integers OK. An order of K is a subring of OK that spans OK over Q and is a Z lattice in OK. Another way of saying that is it's an additive free abelian group that's generated by a basis of OK over Q. Okay, so take a minute to digest that. Proposition 17. Although this could reasonably be called a theorem, it's very important. The image of TF and KF. So what I mean is you've got this isomorphism up here. Okay, but then I've also got the tensor map, TF to the tensor. So the image of TF and KF. Okay, what is that? Turns out to be an order of KF. And VLAF is a free module of rank 2 over QL tensor TF. And I'll let you think about what that means based on some things I've said in previous videos. But I'll spoil it at the end of this video. Okay. The real takeaway, though, is from this, you can conclude that AF is an abelian variety, and I can tell you its dimension. Its dimension is, it's remarkable. It's very simply the degree of KF over Q as a number field. It's just the degree of the field extension. Okay. And so AF is an elliptic curve then, if and only if the Fourier coefficients of F are rational, R and Q. You can see that from just this statement, right? Okay. It'll be of dimension 1 if and only if this degree is 1, but this degree will be 1 if and only if KF is just Q, but KF is Q would join all the Fourier coefficients of F. And so those Fourier coefficients would have to be rational, right? Okay, proof CCSS chapter 3. I also like Diamond and Sherman chapter 6. Let's give a quick connection to modularity. We'll see momentarily, and by momentarily I mean in a future video, that this proposition gives us a map from the set of weight 2 Newforms on X0 of n with rational coefficients to isogeny classes of elliptic curves over Q with conductor n. And what the modularity theorem asserts is that this map is a bijection. Okay, so this should all sound familiar to you if you've been keeping up on all the videos. Okay, I'll end today with just a list of other nice to know facts about AF that I got from DDT, and I'll give you references for proofs. First, if F is an eigenform of level n and P is a prime that doesn't divide n, then AF has good reduction at P, period. Now let's let P again be a prime that doesn't divide n. Let's denote by NFP the number of points on AF when you reduce it mod P. We know that makes sense because AF has good reduction at such a prime. Then NFP turns out to be the field norm associated to the field extension KF over Q of the element lambda of F times 1 minus APF plus diamond of P times P, where lambda of F is the eigenvalue of F at P with respect to the Hecke operator T sub P. Okay. And APF is the P Fourier coefficient of F, of course. Okay. So number 3, which you can just get from number 2, if APF equals E is an elliptic curve, that is, if F has rational Fourier coefficients and F is associated to gamma sub 0 of n, as per the above result, then the number of FP points on E, so the number of points on the reduction of E mod P, is just P plus 1 minus AP of F. Okay, very simple formula in the case AF is an elliptic curve. 4, if F is a Newform of level n, the conductor of AF is n to the G, where G is the genus of the modular curve X sub 0 of n, this should say. This is highly non-trivial. Okay, anytime you're specifying a conductor of a large class of abelian varieties, it's probably a non-trivial result. Okay, the action of GQ on the L-adic rational tape module VL of AF, there's certainly a Galois action on that. We've talked about that a long time ago. It commutes with the action of KF on VL of AF. And that's all just to say there is associated to F a 2-dimensional L-adic representation from GQ to GL2 of OF. Okay, this is essentially just the fact that these actions commute combined with proposition 17, which says that VL of AF is a free module of rank 2 over QL tensor TF. The rank 2 is what gives you ultimately this representation to GL2 of OF. Okay, so proofs. 1 basically is just the fact that the Jacobian associated to whatever gamma that you pick. I didn't say what gamma is, I guess, but gamma here is typically just going to be some congruent subgroup that lives between gamma 1 of n and gamma 0 of n. And it typically will just be one of gamma 1 of n or gamma of 0 of n. In fact, I would say even more typically, it's just gamma 0 of n. Okay. But the Jacobian of the gamma that you pick has good reduction at the primes in question, primes P that aren't dividing n. And that follows from the fact that the modular curve X gamma has good reduction at those primes, which we already talked about a while ago. See the discussion in the remark after the weak form of Eichler-Shimura I gave you in the Eichler-Shimura video, for example. 2 basically follows easily from Eichler-Shimura. I don't remember the details of the proof, but it's easy. Okay. 3 follows immediately from 2 and its proof, and the formula for the L function of AF, which I will give you later in section 3.20. So that's in a future video. Now 4, this conductor, this is probably the most non-trivial result. This is a non-trivial consequence of results from, you guessed it, Carriol, the conductor master, and also from Maser-Stevens. Okay, so I gave you references to the papers here. And then 5 is covered in detail in kind of a lot of different places, but I just like Diamond and Sherman chapter 9. I also like DDT page 85. Okay. And so next video, we will be talking about the converse to modularity in the context of all the stuff covered in this video. So I'll see you then, and thanks for watching.